Okay, so we're in chapter 5 now, and we're looking at first sequences, and then later on we'll be looking at series. And so we started by introducing the concept of a sequence, and you can see that a sequence is simply a string of numbers that have an index, typically starting at 1, but sometimes it starts at 0. It depends on the application that we're using. But this is a standard sequence, and so these terms typically have a pattern between them that we'd like to be able to identify. And so there are different types of sequences. I quickly reminded you about the famous Fibonacci sequence, for example. And this one is a specific type of sequence, which is called recursive, because each term depends on the previous two terms. They're not just randomly generated here. For example, the 2 is the sum of the previous two terms, 1 and 1. The 3 is the sum of the previous two terms, 1 and 2, et cetera, et cetera. And so this is something that you probably heard about before. We're not going to spend a whole lot of time with these types of sequences, but there are many different types of sequences that we could create. And also here, I mentioned right here, formally we write it as an equals an minus 1 plus an minus 2, which means that whatever term we're looking at, it is equal to the sum of the previous two terms. So in other words, whatever n is, n minus 1 is the term before that, and n minus 2 would be the term before that. We can write a sequence in a very compact way in the following, this notation here. We have that an, which represents a term, and of course the term that it is determined by the index n. So n will range everywhere from 1 to infinity, which is what you normally see. But like I said, you could have other starting points as well. 0 is a common choice. Once in a while, you might even run some negative indexes, but only for very specialized circumstances. Anyway, so we did mention that when we have n's ranging from 1 to infinity, we can think of the sequence as being a function where the domain is the so-called natural numbers, meaning the numbers 1, 2, 3, 4, 5, up to positive infinity. And then the range would be whatever values the a's can take on. If we start with 0, then the domain becomes the so-called whole numbers, which essentially are just the natural numbers with the 0 added to it. Now, we sometimes run across sequences that have a very obvious pattern to them. Like here, we've got 2, 4, 8, 16, 32, 64. And if you look at the indexes 1, 2, 3, et cetera, you can see that each term is actually nothing but 2 to the n power. Okay, so the first one is 2 to the first, 2 to the second, 2 to the third, which gives us 2, 4, 8, 16, et cetera. So we can predict or identify any term we choose with this formula 2 to the n, which means that, for example, the 10th term, A10, would be 2 to the 10th, which is 1024. Okay, so the great thing about having a pattern like this is that we can write it out as a formula, and then we can figure out any term that we need just by this very simple formula. And then you can see we can actually express the sequence just by putting the formula in the braces here and identifying the indexes, everything from 1 to infinity. And of course, then, as I mentioned before, the so-called recursive or recurrence relations are ones where each term isn't derived from a function as such, but from the values of the previous terms. And by the way, sometimes a function can be expressed, or a sequence rather, can be expressed in multiple ways. It's not the case that there's only one way of expressing it. Like here, if you notice, this sequence, 2, 4, 8, 16, 32, is the same as this one. But here, we're expressing it as 2 to the n for every index from 1 to infinity. But here, if you notice, it's the same sequence, but we're writing it a little differently. We're showing all the terms past A1, in other words, starting here, as equal to double the previous term. Okay, so for something like this, you would then have to specify what A1 is. You'd have to specify that A1 is 2, and then after that, all the remaining n's are determined as 2 times an minus 1. And so this is an alternative way of expressing the same exact sequence. So it's often the case that the same sequence can be expressed in multiple different ways. None of them is like the correct one. It's just that you'll use the one which makes the most sense for whatever application you're working on. And again, we notice that the sequence doesn't have to start at 1. It could start at 0. This is often the case when the index refers to time, because then it's often the case in practice that a time of 0 is meant to indicate today, and then a time of 1 could be, for example, next year, and a time of 2 would be the year after, etc. So when we're dealing with time, it's not that unusual that the index starts at 0. Anyway, so we identified 2 basic types of sequences that we'll see quite a bit. Not all sequences, of course, fall into one of these 2 categories, but many of them do. And so we have arithmetic sequences and geometric sequences. Now, the arithmetic ones are the ones where, no matter where we start, all the terms after that are calculated with what we call a common difference. Okay, in other words, whatever we started with, we keep adding this common difference to get to the next term. So for example, in this first case, to go from 1 to 2 to 3 to 4, each time I'm simply adding 1. All right, in the second case, I started 2, and each term following that is simply 3 added to the previous term. And in the last case, because the sequence is declining, it's clear that the common difference is negative. So it turns out that with an arithmetic sequence, we can express it in a general form right here, where what it's saying is that, at least in this example, we specify the first term, and then for every term after that, an equals an minus 1 plus the common difference of 1. So this formula can be used to generate any term I need. So if I needed, for example, a10, it would be a9 plus 1. But then we could go through the whole list and we discover that this one is equal to 10 because this one would be 9. Or we could also, actually, no, for this one, you could just literally write it as n. Well, that would be easy. If you want to write it out as a formula, it would be the simplest thing in the world to just call it n. All right, and then we have these other 2. So the thing that they all have in common, again, is that they have a common difference. So for example, here, the starting term, or the first term, is a1 equals 3. Remember, these are indicated as a1, a2, a3, etc., etc. Okay, then we see that the common difference is 4, because we have to add 4 to get to the next term. And so this is the formal way of writing something like this. You've got the first term. We have to specify what the first term is. And then we have the recurrence relationship here. Whatever each term is after that, it's equal to the previous term plus 4. Okay, so in other words, this only applies to terms 2 up to infinity. The first term we have to specify. After that, each one is a function of the previous one. So again, we could use this to figure out any given term. Now, in general, we can express any term in the following way. Here, the formula that we have here only helps us look at the previous terms. This formula says it doesn't matter where you are in the sequence. This is always going to be true. So in other words, if I have 3, 7, 11, 15, 19, 23, and I want to know the 4th term, whatever the starting point is, which is 3, and I'm looking for the 5th term, the 4th term, so the n is 4. The common difference, as you can see, is 4. I'll have 3 plus 3 times 12, 4 rather, equals 3 plus 12, and so we'll end up with 15. And I can find any term I want this way. Now, sometimes what we need is not to identify a particular term in a sequence, but we may be interested in knowing the sum of the first n terms. Now, you can see the number of terms is fairly large. This is going to take quite a while. So this formula is an alternative to doing it that way. It's a very nice compact formula. And so you can see Sn is the sum of the first n terms. Sometimes this is called a partial sum, by the way, because we're not considering all the terms out to infinity, only the first n. N itself is the number of terms we're looking for. A1 is the first term, an is the nth term, and then we divide all that by 2. So using this formula, we may have to figure out for ourselves what an is. A1 has to be given to you in the problem. An, we may have to do that ourselves. So let's take a look at this case. The sequence is 1, 3, 5, 7, 9, 11. So the first term is 1. The common difference is 2. And so if we want to know the sum of the first 5 terms, we need to know A5. And you can see by just looking at these that it certainly is the 9, but what you could also do is use this formula. A1 is the 1. One plus 4 times 2 is equal to 9. So we can count it, just go 1, 2, 3, 4, 5, or we can just use this formula to find the nth term. Once we have the nth term, then we can come back up here and just plug everything in. So we've got 5 for n because we're looking for the sum of the first 5 terms. 1 is this A1, 9 is A5. We divide by 2, and you'll see that it's 25. And you can double check that, of course, just by adding them up directly, and you'll end up in 25. Okay, now, here's an example. What about the first 100 terms? Well, the time involved doesn't really matter if it's 1 term or 500 terms or 1,000. Let's say this is our sequence. It's clearly an arithmetic sequence where A1 is 1, and the common difference is also 1. I want to add up the first 100 terms. So S100 is n, A1 plus an over 2. N is 100. Here's A1, here's A100. We add them up, divided by 2, and we end up with 5,050. See that how quick that was. Now, by the way, there's an interesting reasoning behind this. Let's take a quick look. Here's your first 100 terms. So we already saw that the sum of the first 100 is 50/50. And we've seen that the reason why this is the case is because we have n, A1 plus an over 2. So here's how you have to visualize this. If you took the first and the last terms, you'd have a sum of 101. If you took the second to the last, and the second and second to last, they add up to 101. And if you keep doing this enough times, we'll see that there are 50 pairs of numbers, each with a sum of 101. So therefore, the total, 101. The total has to be 50 times 101, which is 5,050. And so that's really where this formula is coming from, because it's saying you got 100. The 2 is here. 100 over 2 is 50. So this is the sum of each pair, and this is the number of pairs. Okay, so that's the basic logic behind this formula. All right, well, anyway, how about this one? There's another arithmetic sequence that starts with 8, it has a common difference of 2. What's the sum of the first 6 terms? Okay, well, let's plug everything in the formula. You can see it already has all 6 of them here for us. We don't have to figure out A6 ourselves. So we have 6 for n, A1 is 8, A6 is 18 over 2, and you end up with 78. Again, you've got 3 pairs with a sum of 26. Okay, very good. Now we're ready for geometric sequences. So the difference here is that instead of each term being separated by a common difference, meaning that we're adding to each term now is separated by a common ratio, which means we're multiplying. Okay, so in other words, instead of something like this, where we have a common difference of 2, with a geometric sequence, you'd have something like this. So we're clearly multiplying each term by 2. We're not adding, we're multiplying. And so we say that the common ratio is 2, which means that an equals r times an minus 1. So we go through the entire sequence, and no matter what term we're looking at, it is equal to r times the previous one. So that's the difference between arithmetic and geometric. So like in the first, here we see that r is 2, here r is clearly 3, and here r is 5. You should be able to tell just by looking at a sequence if it's geometric, because it changes very quickly compared to the arithmetic sequences. Now, I do want to mention here that the ratios do not have to be positive integers. Imagine you had something like this. Well, in this case, the common ratio is -2. And then how about this one? Well, it should be clear that the common ratio, since the numbers are getting smaller, but they're not negative, the common ratio is simply a fraction, which is 2. Okay. So in the first case, if you notice the signs are alternating, which is a sure sign that the common ratio is negative. But in the second case, the numbers are simply getting smaller, and they end up having a common ratio of 1/2. All of these are geometric sequences. Now this one, we can write it as a recurrence relationship as follows. And it'll be very similar to what we did before. All right, so remember, it was 2, 6, 18, 54, 162. So that means we started with 2, and after that, all the terms from 2 on are found by multiplying the previous term by 3. Okay? So that's what this means. This implies that the common ratio is 3. The way it's written, the common ratio is 3. Now, in general, this is a formula that'll let you identify any term you need. If you know the starting point and the common ratio, you can find any term you want with this formula. Except for, this is for 2 and up, of course. So let's look at a quick example using this one we just had before. This is A1, A2, A3, A4, and A5. So if I need to know the fifth term, which obviously I can see it, but if I want to figure it out with my formula, I've got A1, which is the 2. The common ratio is the 3. And the exponent is n minus 1. In other words, 4. I've got 2 times 3 to the 4th. That turns out to be 162. So it's a very straightforward formula. And if you notice, we don't need to know anything else, just the first term and the ratio. Very convenient. So you can imagine these will pop up a lot in practice. For example, if you're looking at the balance in a bank account, the growth rate will follow something very similar to this. Or imagine if in science you're looking at the population of some city or other, the growth of the city population would follow along a sequence like this one. But anyway, there's a formula here for the sum of the nth terms, first n terms, just like before, except this time you can tell this is not an arithmetic sequence because it contains this r. It's a little messier than the case for the arithmetic sequence, but it's not that complicated considering that you're adding up a group of numbers that are growing very, very quickly. So here's an example. Let's say we're looking to sum up the first 4 terms of this clearly geometric sequence. Okay, how do you know? Because the first term is 5, which tells us nothing, but the common ratio is clearly 2. In other words, to get from 5 to 10, we have to multiply by 2, 10 to 20, etc., etc. So S4 would be 5, 1 minus 2 to the 4th, over 1 minus 2. 2 to the 4th is 16. Now, these two negatives will often drop out. Okay, I mean, here we only have positive terms. We can't possibly have a sum of that adds up to a negative number. So often we see the negatives drop out in these cases, and then we just simply end up with 75. Wait a minute, did I do that right? That doesn't look right. Oh, yes, because we're only, God, that scared me. We're only looking at the first 4 terms. Yeah, that's it. Okay. Yeah, that's 75. So it's pretty straightforward. It can get messy, but especially if you've got like a fractional ratio or a negative ratio or something along those lines. All right, now you can probably imagine that at some point we have to bring back the concept of the limit, because these sequences are going to go on and on for until infinity. And so what we're often interested in is the limiting behavior of these sequences. In other words, is it the case that if you drew all the terms in the sequence, like for example, the one that had 1, 1/2, 1/4, 1/8, etc., etc. If I were to plot that out, here's 1, here's a half, here's a quarter, here's an eighth, here's a 16th. What we're interested in is determining if these terms are actually converging to some constant value. Now here it looks like they're getting awfully close to 0. But if you have something like this, they're just getting enormous very quickly. So it's pretty clear that in the second case, the terms are not converging. or we could say that they're converging to positive infinity. But in the first case, it looks like they're heading towards zero. So what we would like to be able to do is find out whether the sequence is converging to a specific value or not. So that means we're going to need to use limits. Okay, so the limit of a sequence, if the terms converge to a specific value, meaning a constant of some kind, as n approaches infinity, the sequence is said to be convergent. Otherwise, it is said to be divergent. Okay, that's all we have. And you can see here, it means this sequence is convergent. And this one is divergent. It's just going to grow forever. Okay. Eventually it'll reach infinity, or at least it's heading towards infinity. Now, if the sequence is in fact convergent, we can use limits to find out what it converges to. All right. So if we have a sequence AN, like we have been looking at, and that AN is a function of N. Okay, so like for example, I could rewrite this as because the first term would be 2 to the 0 power, 1 over 2 to the 0 power. The second term would be 1 over 2 to the first power. And then the third term would be 1 over 2 squared, et cetera, et cetera. So that being the case, clearly the terms are a function of n. And then further, then there's some L that we can calculate with the properties of limits that the sequence is converging to. If their number exists. In other words, they're not guaranteeing that this exists, by the way. They're saying that if it does exist, then the limit of the sequence would give us that number. That's what they're basically saying. They're not saying, don't worry about it. They all have a limit. They don't. Clearly, the divergent sequences do not, but the convergent ones, they do. And so, in other words, we can sometimes determine if the sequence is convergent or not in the first place by finding the limit. Because sometimes it's not that obvious if a sequence is convergent or divergent. So calculating the limit means that it is in fact convergent, and on top of that, we know what it converges to. Otherwise, if we can't find a limit, if it doesn't exist, that means that the sequence is divergent rather. Okay, so there's the limit of that sequence is the L. All right, let's look at some examples. So here's our first sequence. It's clearly an arithmetic sequence where A is 1. A1 is 4 rather, and the common difference is 3. Now we already know that we can write this in the following way. So what that means is this one is not converging because it's just continuing to grow forever. So in other words, if you plotted this out, well, it's going to be hard to do this. I don't know if SimpleLab is capable of drawing. You know what? I never thought about that until just now. Let's see if SimpleLab can draw a sequence. I'm not so sure. I mean, that sounds kind of advanced, but let's see what it can do. It might be fun to look at some of these. See, it has an arithmetic sequence calculator, apparently. I'm not sure what to do. um, it's not offering to let me just type in a bunch of numbers, is it? All right, I'll tell you. Let's. Oh, all right. I think here it's saying, tell me some numbers, and I'll tell you the formula. Okay. Yeah, but you see, it's not offering to draw the graph. But you can imagine, I mean, if you just kept, if you did plot this, oh, for God's sakes, you know what? Let's do this in Excel. Now, the beauty of Excel, Excel has a feature that you may not even know about. It can spot patterns too, simple patterns. And if I tell it, for example, I have the numbers 4, 7, and 13. I can actually select the whole group and then drag it down, and you'll see it'll fill them in correctly. You see how it's just keep adding 3. And now I just want to plot this. And what we're going to notice, yeah, I mean, it's pretty clearly not converging. It's just going up by 3 every time n goes up by 1. So why don't we try that other one I was trying to draw before? Let's see how it handles this one. Oh, all right. See, now what I should have done, yeah, kind of disappointed here. I'm going to do the formula I had 2 raised to the n minus 1 power. It's got 1, a half, a quarter, an eighth, a 16th, etc. So when I plot this one, yeah, now we're talking. Look at that. It's pretty obvious that this one is converging to 0. So while this isn't technically a function, it's just a series of individual observations. Excel is filling in the gaps for us, but you can see where it's going. So we can't take the derivative of this function because it isn't a function, not really. I mean, we know there's no equation that we could use. Okay, well, I mean, it's not, all right. It's fine the way it is. Now, oh my God, look at this one. Now, this one is neither anyway. I mean, look at this thing. It just goes back and forth and back and forth and back and forth between 1 and -1. So it is not convergent. It's never going to reach some limiting point. And it's clearly not arithmetic or geometric. Now, how about this one? This one looks interesting. It turns out this one is the result of 1 minus 1/2 to the nth power. Okay, so in other words, when n is 1, we'll have 1 minus a half. When n is 2, 1 minus a quarter. When n is 3, 1 minus 1/8, etc., etc. And you can see they're getting awfully, awfully close to 1. It looks like this sequence is converging to 1. So if we take the limit of this as n goes to infinity, or x goes to, oh, wait a minute, sorry, this should have said n. All right, I will be making a note to myself to fix that. Okay. That should have been an n. All right. But the idea here is that when n goes to infinity, this goes to zero, okay? Because n keeps getting larger and larger. As n gets larger, a fraction like that will continue to get smaller. So this is equal to 1 minus 0, or just 1. And so, to nobody's surprise, this sequence is converging to 1. But the thing is, with the limit, we can prove what the exact value is. We can look at the graph, and that's fine, but we want to have a formal way of doing this. And this is it, by taking the limit as the index goes to 0. All right, now, just because we're probably going to need these, we're going to have a quick review here of limit laws, as they're called. So we have two sequences, which we're just going to write in with this notation. The index almost doesn't matter. I don't think it affects any of these results, so we'll just leave it like this. And some constant c, which is a real number. If, now, by the way, what you're seeing here tells us that this converges to A, and this sequence converges to B. That's what those actually mean. Then we have the following, and these are very much like the laws we've seen before when they were applied not to sequences, but the x and functions of x. So the limit of a constant is the constant. Now here I can factor out the c, and then just this piece, by definition, is equal to a, and therefore we just have ca. Okay, that's because we chose that on purpose. We were told that that sequence has a limit of capital A. What else? Oh, and again, these are pretty self-explanatory. The limit of a sum is the sum of the limits. Even though these are sequences now, the rules are still the same. Same thing with the products. We end up with A, B, and then the ratios, of course, assuming B is not 0. So there's nothing new here. It's just that we're applying limits for the first time to sequences rather than functions of x and constants. All right, let's look at this one. Oh, so you see, this is a good example. How do you know by looking at this? Let's see if we can turn this into a function and graph it in Symbolab. It might give us a hint as to what we can expect when we take the limit. So we have 5 minus uh, 3 over, let's call it x squared. And let's see what the graph looks like. Well, it appears that no matter which direction they're coming from, there appears to be an asymptote here at y equals 5. And you can see why. If x keeps getting larger and larger, then we're subtracting a progressively smaller term here. And so you can see there's an asymptote here at 5. So that's kind of a hint. And also, just a quick reminder, algebraically, the limit of n as n goes to infinity of 1 over n, or to any power for that matter, whenever you have a constant like that, divided by a variable that's growing very quickly, they're all going to equal zero. Because you're dividing by a progressively larger number, the numerator never changes. So what that means then is that this is equal to zero. Another way to look at it is that the limit of 1 over n squared is the limit of 1 over n times the limit of 1 over n. And that gives us 0. So now here, we can break this one up into two pieces. We have the limit of 5 by itself minus 3 times the limit of 1 over n squared, which is 5 minus 3 times 0, which is just 5, as we predicted. Okay, you can see from the graph that there's an asymptote right there at 5. So clearly the function is converging to 5 as n approaches positive infinity. Okay, in other words, as we keep moving in this direction, the function is getting very close, but never quite actually touching 5. Okay, here is a tricky one. So let's take a look at the graph. Cosine of 3 over x squared. Oops. Now, my suspicion is that this one is not convergent at all because the cosine goes through a series of repeated waves. Oh my God. Maybe not. Look at that. That's a strange function. I mean, recall that just cosine by itself is a repeated series of waves. Yeah, you can see it repeats. So it's clearly not converging. So here, this one is different because we're dividing out by n squared. Let's go back to that graph again. Yeah, you can see there is an asymptote here, 1. So as x approaches infinity, this function is approaching 1. So here, once again, we have the n squared. And we know that the limit of that is 0. And so basically, what you've got here is actually, this is, you know what I just realized? This is a L'Hopital's rule case because you're going to wind up with infinities here. So if you take the derivatives, no, hold on. Oh, no, no, no. All this, it's not as, I'm just making it too complicated. This is, oh yeah, here we go. There's this, oh, no, hold on. Let's try that again. As n goes to infinity, this term goes to 0. So, um, no, sorry, let's try that again. We do not move the 3 outside. The ratio itself is going to 0. That's the important thing. The ratio, the limit of this ratio is 0. So we have the cosine of 0, and that's where this is coming from. Okay. No, I couldn't see. The thing is, I couldn't move the 3 outside here because it's the cosine of 3. Okay, so in other words, this has to stay intact as a single ratio. And so if the limit of 1 over n squared is 0, it stands to reason that the limit of 3 over n squared is also 0. Okay. So here instead it's cosine, and so we end up with 1, as the graph shows us. All right, now we got some theoretical results. Before we do that, let me show you the graph that this is building up to. What they've done here is they have sequences A and B, a C rather. Now, both of these sequences have the same limit, which is L. So basically what the squeeze theorem is saying is that if for every n, actually, I just realized I put the wrong one here. It's A is the larger one on the top, C is the one on the bottom. Okay, this is better. If for all n, B is in between the two, which you can see in this graph. No matter what A is and what C is, B is always in between them. Then it must be the case that the limit of B of n is also equal to L. Now, how does this help? Because sometimes you might have a function that you're trying to take the limit of, and it's very, very scary and very complicated. And then, like here, for example, what if A and C are both insanely complicated, but we can find a function or sequence B that's always in between the two of them, and it is a lot simpler. Then we may want to take advantage of that and come up with the limit of B. And then we know that that's equal to the limits of A and C. So this is just something that's available to us if we need it. You don't go out of your way to apply the squeeze theorem unless you really need it. Okay, so here's the more formal statement of it. Yeah, I mean, also, yes, I just want to point out that it's possible that this behavior doesn't start right away. That, I mean, here, this is true for all n's, as you can see. But if there's some point after which this is true, they're still going to end up having the same limit. Like, let's say if you had something like this. A is, and then B is, and then this is actually C. And then let's just say B is So in other words, what I'm trying to illustrate here is that there's a region within which Bn is actually greater than An, but after a certain point, let's say right about here, we can think of this as capital N. So in other words, for all lowercase n, for all greater than or equal to this capital N, the An the Bn rather is in between the two. Then the squeeze, then they all, and here's L, have the same limit. L. Even though the sequence Bn isn't always in between. Once we get past a certain point, it always stays in between the other two. So that's good enough. It still means that they all are converging to the same limit. All right. Now here's an example when you have a really scary formula. Look at this thing. We want to find its limit if it exists. So what we're going to note here is that if you look at the cosine of any value, let's go back here. Let's look at the graph. If you notice, the range is only the values between negative and positive 1. Notice it never goes below negative 1. It never goes above positive 1. So that helps us with the squeeze theorem. Now, suppose we don't want to deal with this messy function. What we do know is that cosine of n is bounded between negative and positive 1, which implies that no matter what n is, the same thing can be said for negative 1 over n squared and positive 1 over n squared. So this must hold. And what that means then is that the limit of these outer terms are equal to each other, and they're both equal to 0, which implies that this limit is also equal to 0. So in other words, we're able to find two simple sequences that bound the one we were looking for. And we were able to show that thanks to the squeeze theorem, we don't need to deal with cosine n over n squared. Instead, we can simply show that it must be 0 because that is the limit of negative 1 over n squared and 1 over n squared, which are guaranteed to bound this function. Now, having said all that, let's look at the graph of cosine n over n squared, or in this case, x over x, cosine x over n x squared, let's say. Oof. But you can see, even though the pattern is gyrating up and down above the horizontal axis, it appears to be getting very, very close to 0 as x converges to infinity, or x approaches infinity. The function is it's going up and down and up and down, but you can see it does have an asymptote here. Although unusually for an asymptote, it's going above and below it, but it is converging to that asymptote. Wow. Yeah, so Now we're going to consider this notion of bounded sequences. A bounded sequence simply means there's some upper value that the sequence will never rise above. If we can find such a number, m, then we say that the sequence is bounded from above, meaning there's some value it will not go above. No matter what it looks like. Or if it's going up, there's some value within outside of which it will not fall. And the same thing is true from below. It can be bounded from above, it can be bounded from below. What that implies then is that there's some limit. In other words, it doesn't diverge. And so here, what we're going to say is that if a sequence is bounded from both above and below, it has to be both, then it is bounded. If not, we simply say it's unbounded. And therefore, as I've said, the purpose of this is to recognize that if a sequence is bounded, it must have a limit, which means it must converge. Okay, so we can prove that a sequence converges because it has either it has an upper and a lower bound. Then we can also prove that it must have a limit. Of course, it would be nice if we could find that limit, but at least we know that it exists. Okay. Anyway, so we got just we're very close to the end here. Let's just wrap this up. A sequence can have a lot of patterns to it. You can have anything you could imagine. But like you could have something like that. What we're seeing here is, in some cases, the sequence continuously increases for every time n increases, like something like this. We fall into this category, no matter how far out we go. And I mean, it never decreases. Down here is the other way around. As n continues to increase, the function will never increase again. Or actually, I shouldn't say this function, the sequence will never increase. So this means that this sequence is increasing and this one is decreasing. Increasing means it never goes down. Decreasing means it never goes up. Now, by the way, though, this does allow for the possibility of staying the same. You see how it's greater than or equal to, sorry, wrong one, less than or equal to and greater than or equal to. So in other words, 1, 2, 3, 4, 5, 5, 6, 7. There's a tie here between 5 and 5. We still call this increasing because it never actually went down. And with a decreasing, we have something like this. And again, there's a tie here, but it never actually went back up again. So this one is still qualifies as decreasing. Now, by the way, if you want to avoid that, here's what will end up happening. Like, in other words, if you only are interested in a sequence where it always, always, always goes up, something like this, then the adjectives are a little bit different. Instead of calling it increasing, we call it strictly increasing to indicate that there's no exceptions. And then something like this is strictly decreasing. And you never know when this might come in handy. It turns out, for example, a function that is either strictly increasing or decreasing is guaranteed to have an inverse. So, this kind of information can be very useful. Now, if it falls into one of these two categories, increasing or decreasing, we say that it is monotone. Sometimes, though, you also hear the increasing functions called monotonically increasing. And of course, that implies that something like this would be referred to as monotonically decreasing. It means, well, all right. It just simply means it always does one or the other. Okay. Now, there's a convergence theorem for this, of course. So basically what it's saying is that if AN is bounded, meaning there's an upper and a lower maximum value, or a lower maximum minimum value, then there must be some point along our sequence after which it is monotone and it converges. Okay, in other words, even if the pattern is different up front, when it reaches a certain value n0, from then on, it only increases, or possibly it only decreases. Then it is said to have, it converges in spite of its strange behavior back here before n0 was reached. Okay, so this is guaranteed to converge. Okay, and then there's a nice graph on the next page that shows you something like that. It just, you can see it's going up and up, but it's increasing in such a way that it's flattening out and eventually reaches this asymptote. It never goes above that point. And so this is what it converges to. This, let's call this L. All right, so that's 5A. These were all sequences. What's coming up next in the second half of this chapter is series. And series are basically derived from sequences in a very unique way. So we're going to look at that next time. Okay, so see you then.